October 8, 1945. The second floor of Building 5 at Raytheon's manufacturing plant in Waltham, Massachusetts hummed with the familiar electric thrum of wartime engineering. Percy Spencer stood before a magnetron, a vacuum tube that generated the microwave radiation powering Allied radar systems, his weathered hands adjusting dials with the practiced ease of a man who had built thousands of these devices. The war in Europe had ended 5 months earlier, and Japan had surrendered just weeks ago, but the production lines still ran, fulfilling contracts, testing improvements, preparing for whatever came next. Spencer, at 51 years old, had spent the war years transforming Raytheon from a small radio tube manufacturer into a powerhouse of military technology, and now, in this moment of global transition, he stood at the threshold of an entirely different revolution. He reached into his pocket for the Mr. Goodbar candy he had tucked away that morning. A small indulgence, a sweet reward for the long hours. His fingers touched something warm. Too warm. Confused, he pulled out what remained of the chocolate bar, now a melted, sticky mess coating the wrapper and threatening to drip onto the pristine floor of the laboratory. For a moment, Spencer simply stared at the molten candy, his engineer's mind already racing through possibilities. The room was not particularly hot. He had not left the candy near any conventional heat source. Yet something had generated enough thermal energy to liquefy the chocolate completely. His eyes moved to the magnetron, its metal casing warm to the touch, its internal components generating powerful pulses of electromagnetic radiation at a frequency of approximately 2.45 gigahertz. Could the invisible waves emanating from this device have heated his candy? The hypothesis seemed improbable, almost absurd. Electromagnetic radiation was not supposed to heat objects in this manner. Everyone knew that heat came from flames, from electrical resistance, from friction. But Percy Spencer had learned long ago never to dismiss an anomaly, never to assume that conventional wisdom held all the answers. To understand why this melted candy bar would change the world, we must first understand the man who noticed it, and more importantly, the man who refused to let the mystery pass unexamined. Percy LeBaron Spencer was born on July 19, 1894, in Howland, Maine, a tiny logging community where poverty was not an exception but a way of life. His father died when Percy was just 18 months old. His mother, unable to care for him, sent him to live with an aunt and uncle. When Percy was 7, his uncle also died, leaving the boy to become the man of the house far earlier than childhood should have ended. He left school after the 5th grade, not because he lacked intelligence or curiosity, but because survival demanded it. He worked in a spool mill from dawn until dusk, 12 to 14 hours a day, earning money to help support his aunt. At age 12, Spencer heard that a paper mill in the nearby town was installing electricity, a marvel of the modern age, still rare in rural Maine. The boy walked to the mill and asked for a job, any job, just so he could watch the electricians work. He became an apprentice of sorts, learning by observation, asking questions, absorbing knowledge with a hunger that formal education had never satisfied. When he was 16, he heard that the U.S. Navy was looking for wireless operators, men who could understand the mysterious art of radio communication. Spencer enlisted despite having no formal training, no credentials, no reason anyone should believe he could master such technical work. Yet he taught himself radio theory by reading every manual he could find, by experimenting, by refusing to accept that his lack of formal education should limit what he could understand. During World War I, Spencer served on the USS Huntington, learning not just radio operation but the deeper physics of electromagnetic waves, the mathematics of signal propagation, the engineering principles that transformed abstract theory into functional technology. After the war, he continued his self-education, taking correspondence courses, reading technical journals, building his knowledge one concept at a time. In 1925, he joined Raytheon, then called American Appliance Company, as a tube designer, bringing with him an unusual combination of theoretical understanding and practical skill. By the time World War II erupted, Spencer had become one of Raytheon's most valuable engineers, a man whose unconventional path to expertise had given him insights that formally trained engineers sometimes missed. When the British desperately needed magnetrons for their radar systems, devices that could detect German aircraft at night and through clouds, devices that would prove crucial to winning the Battle of Britain. Spencer transformed the production process. The British magnetron, invented at the University of Birmingham, was a revolutionary device, but manufacturing it remained painfully slow, with skilled workers handcrafting each component. Raytheon could produce only 17 magnetrons per day when Spencer began working on the problem. Within months, Spencer had redesigned the entire production process, finding ways to automate what had been manual, to standardize what had been custom. He understood the magnetron not just as a piece of laboratory equipment but as a product that needed to be manufactured at scale, with consistency, with speed. By 1943, Raytheon was producing 2,600 magnetrons per day, and Percy Spencer held the title of senior consultant. The company's recognition that this self-taught engineer from rural Maine had become indispensable to the war effort. He received the Distinguished Public Service Award from the U.S. Navy, one of the highest honors a civilian could receive for contributions to naval technology. Now, on this October afternoon in 1945, with the war over and the urgency of military production fading, Spencer stood with melted chocolate on his fingers and a question burning in his mind. Rather than dismissing the incident as a curiosity, he decided to test his hypothesis. He walked to a nearby storage area and returned with a bag of popcorn kernels, the kind that employees sometimes popped on hot plates during lunch breaks. Spencer placed the bag near the magnetron, powered up the device, and waited. Within seconds, the kernels began to pop, not from the outside in as they would in a conventional fire or hot oil, but from the inside out, heated by the microwaves penetrating the kernels and exciting the water molecules within. Popcorn scattered across the laboratory floor, and Spencer began to smile. The next morning, Spencer arrived at the laboratory with an egg and a kettle. He placed the egg in the kettle, cut a small hole in the shell, and positioned it near the magnetron. A colleague, curious about what Spencer was doing, leaned in to watch. As the magnetron powered up, the egg began to tremble. The microwaves penetrated the shell, heating the contents rapidly, building pressure. Suddenly, the egg exploded, splattering hot yolk directly into the colleague's face. Spencer, now certain of his discovery, could not stop laughing even as he helped clean up the mess. The microwaves were heating food, heating it from the inside, heating it faster than any conventional method. The military applications were immediately obvious. Soldiers could heat rations without building fires that might reveal their positions. But Spencer's mind raced further. Could this technology transform cooking itself? Within days, Spencer began designing the world's first microwave cooking device. He constructed a metal box to contain the electromagnetic radiation, ensuring that the waves would bounce internally rather than escaping to heat other objects or potentially people. He installed a magnetron from the radar production line, added a power supply, and created a simple door mechanism. The first prototype stood nearly 6 feet tall, weighed 750 pounds, and cost about $5,000, roughly equivalent to the price of a new house in 1945. It was not practical for home use, not yet, but it proved the concept. On October 8, 1945, exactly 1 year after the candy bar incident, Spencer filed a patent application for a method of treating foodstuffs, describing a process by which microwave radiation could rapidly heat food without requiring any direct contact with conventional heat sources. Raytheon, recognizing the commercial potential, immediately began development of a marketable product. In 1947, the company unveiled the first commercial microwave oven, called the Raytheon, a name that directly referenced its radar technology origins. The Raytheon 1161 stood over 5.5 feet tall and weighed more than 700 pounds. It required plumbing because the magnetron needed water cooling to prevent overheating during extended operation. The price tag remained prohibitive for most consumers, approximately $3,000, or about $35,000 in current purchasing power. Only commercial establishments, restaurants, railroad dining cars, cruise ships, and luxury hotels could justify such an investment. The early adopters discovered both the promise and the limitations of microwave cooking. The Raytheon could heat food in minutes rather than hours, a revolutionary improvement for food service operations dealing with high volumes and demanding customers. But the technology had quirks that required learning. Foods cooked unevenly, with hot spots forming where microwaves concentrated. Some materials sparked or melted when placed inside the device. Metal containers, which worked perfectly well in conventional ovens, created dangerous electrical arcs in the microwave environment. The cooking process itself seemed almost magical to those who witnessed it. Food heating without visible flames, without glowing heating elements, through the power of invisible electromagnetic waves. Despite these challenges, Raytheon continued refining the technology. Engineers worked to reduce the size and cost, to eliminate the water cooling requirement, to make the devices more reliable and user-friendly. By 1955, Raytheon had developed the first domestic microwave oven, marketed under the Tappan brand name. This model still cost over $1,000 and found few buyers in a market where most American families considered television sets a luxury purchase. The microwave oven remained a curiosity, an expensive gadget that promised convenience but delivered inconsistent results at a price that made conventional cooking seem perfectly adequate. Percy Spencer, meanwhile, continued working at Raytheon, contributing to the company's expansion into new technologies and markets. He never sought fame for his invention, never gave lengthy interviews about the moment his candy melted, never capitalized personally on the commercial development of the microwave oven beyond his regular salary and occasional bonuses. Those who worked with him described a man of profound modesty, someone more interested in solving the next problem than celebrating past achievements. He held more than 150 patents by the time he retired, covering technologies ranging from radar to metallurgy, but he remained most proud of the magnetron production improvements that had helped win World War II. Spencer's lack of formal education became a point of fascination for journalists who wrote about the microwave oven's invention. Here was a man who had left school after 5th grade, who had taught himself mathematics and physics and engineering, who had competed with university-trained scientists and often surpassed them. His story became part of American mythology, proof that intelligence and determination could overcome the limitations of circumstance, that innovation could come from unexpected places. Yet Spencer himself downplayed such narratives. When asked about his success, he would often respond that curiosity and persistence mattered more than credentials, that the willingness to ask why and how opened more doors than any diploma. The true revolution in microwave cooking would not arrive until the late 1960s, when Japanese manufacturers entered the market with smaller, more affordable designs. Amana Raytheon, a subsidiary of Raytheon, introduced a countertop microwave oven in 1967, priced at just under $500. This model, no larger than a conventional toaster oven, finally made microwave cooking accessible to middle-class American families. Sales began to climb, slowly at first, then exponentially as the price continued to drop and the technology continued to improve. By 1975, annual microwave oven sales in the United States exceeded 1 million units. By 1986, more American households owned microwave ovens than dishwashers. The cultural impact extended far beyond convenience. The microwave oven transformed food production, enabling the creation of an entire industry devoted to prepackaged, ready-to-heat meals. Frozen food manufacturers redesigned their products specifically for microwave preparation, creating packaging that could withstand high temperatures and cooking instructions calibrated for microwave power levels. Fast food restaurants installed commercial microwaves to speed up service during peak hours. College dormitories and office break rooms filled with microwave ovens, creating new eating patterns divorced from traditional meal times and preparation methods. Critics emerged as well, questioning whether microwave cooking destroyed nutritional value, altered food chemistry in dangerous ways, or represented yet another step in the industrialization and degradation of the human diet. Some studies suggested that microwave radiation might leak from poorly sealed units, exposing users to harmful electromagnetic fields. Consumer advocacy groups demanded better safety standards and clearer labeling. The Food and Drug Administration established regulations governing microwave oven construction and maximum allowable radiation leakage. Most concerns proved unfounded or were addressed through improved engineering, but the debates reflected deeper anxieties about technology's increasing presence in daily life. The science behind microwave cooking, while straightforward in principle, involved physics that seemed almost supernatural to many users. Magnetrons generated electromagnetic waves at a frequency of 2.45 GHz, the same frequency that radar systems used during World War II. At this frequency, the waves resonated with water molecules, causing them to rotate rapidly, billions of times per second. This molecular rotation generated friction, and friction generated heat. Because food contains water throughout its structure, microwaves heated food volumetrically, warming the interior and exterior simultaneously, rather than relying on heat conduction from outside to inside as conventional ovens did. This internal heating explained why microwave ovens cooked food so much faster than conventional methods. A baked potato that required an hour in a conventional oven could be cooked in 5 minutes in a microwave. The time savings came from bypassing the slow process of thermal conduction, eliminating the need to first heat the air inside the oven, then heat the surface of the food, then wait for that heat to slowly penetrate to the center. Microwaves simply heated the water wherever it existed, all at once, throughout the entire food mass. Yet this same mechanism created the unevenness that frustrated many users. Microwave energy did not distribute perfectly evenly inside the cooking chamber. Standing waves formed, creating nodes where the electromagnetic field strength was high and antinodes where it was weak. Foods placed at nodes cooked quickly, even scorching, while foods at antinodes remained cold. The rotating turntable, introduced in later models, helped address this problem by moving food through different regions of the electromagnetic field, averaging out the hot and cold spots. Even with turntables, however, microwave cooking required attention to food placement and occasional stirring to achieve consistent results. The materials used in microwave cooking mattered enormously. Glass and ceramic allowed microwaves to pass through essentially unchanged, heating the food inside while remaining cool themselves. Plastics varied depending on their chemical composition. Some were microwave safe, while others melted or released toxic compounds when heated. Metals reflected microwaves, creating electrical arcs that could damage the magnetron and potentially start fires. The specificity of these requirements meant that users needed to learn an entirely new set of rules for a task, cooking, that most people had learned through long experience with fire and heat. Percy Spencer lived to see the microwave oven transition from an expensive curiosity to a standard kitchen appliance, though he never fully appreciated the magnitude of the transformation his accidental discovery had initiated. He died on September 8, 1970, at the age of 76, just as microwave ovens were beginning their explosive growth in the American market. Raytheon, in recognition of his contributions, dedicated the Spencer Laboratory at the company's research facility in Burlington, Massachusetts. The company also established the Percy L. Spencer Award, given annually to employees who demonstrated exceptional innovation and creativity. In 1999, Spencer was inducted into the National Inventors Hall of Fame, joining Thomas Edison, Alexander Graham Bell, the Wright brothers, and other giants of American innovation. The citation noted not just the microwave oven invention but Spencer's broader contributions to radar technology and his embodiment of the principle that curiosity and persistence could overcome any obstacle. The ceremony included testimonials from colleagues who had worked with Spencer, men who described his habit of arriving at the laboratory before dawn, his willingness to spend hours testing ideas that others dismissed as impractical, his absolute refusal to accept that something could not be understood or improved. The global impact of Spencer's invention is difficult to overstate. By 2025, an estimated 90% of American households own microwave ovens. The percentage is similarly high across most developed nations and continues to grow in developing economies as prices decline and electrical infrastructure expands. The microwave oven has become so ubiquitous that an entire generation has grown up never knowing a kitchen without one, never experiencing the pre-microwave era when reheating leftovers meant using a conventional oven or stovetop, when frozen meals required thawing and extended cooking times, when convenience food meant canned goods rather than pre-packaged meals designed specifically for microwave preparation. The technology has evolved dramatically since Spencer's first prototype. Modern microwave ovens include convection heating elements that combine microwave and conventional cooking, sensor systems that automatically adjust cooking time based on humidity levels, and inverter technology that provides continuous variable power rather than cycling between full power and off. Some high-end models incorporate artificial intelligence algorithms that can identify food types and recommend optimal cooking parameters. Yet the core technology remains unchanged, a magnetron generating microwaves at 2.45 GHz, a metal chamber containing the electromagnetic radiation, and a door seal designed to prevent leakage. Industrial applications of microwave technology have expanded far beyond food preparation. Chemical manufacturers use industrial microwave systems to accelerate reaction rates and improve product yields. Medical facilities employ microwave technology for sterilization and for warming for fluids and blood products. Materials scientists use microwaves to cure polymers, to sinter ceramics, and to synthesize novel compounds. The telecommunications industry relies on microwave transmission for long-distance data links and satellite communications. Each of these applications traces its lineage back to the radar magnetrons of World War II and to Percy Spencer's willingness to investigate why his candy bar melted. The story of the microwave oven's invention has become a staple of innovation literature, cited in business schools and engineering programs as an example of how breakthrough discoveries often result from accident combined with prepared observation. The key lesson, educators note, is not that Spencer's candy melted. Many engineers probably experienced similar incidents while working with radar equipment. The lesson is that Spencer noticed, wondered, investigated, and persisted. He could have dismissed the melted candy as an annoyance, thrown it away, and moved on with his day. Instead, he asked why it happened and refused to stop asking until he understood the answer. This attitude, the refusal to accept mystery, the insistence that phenomena must have explanations, characterized Spencer's entire approach to engineering. Colleagues recalled that Spencer would often spend hours examining a failed component, trying to understand not just what went wrong but why it went wrong, what fundamental principle had been violated or misunderstood. He maintained detailed notebooks filled with sketches, calculations, and observations, documents that revealed a mind constantly questioning, constantly seeking deeper understanding. The economic impact of the microwave oven industry has generated hundreds of billions of dollars in revenue since commercial production began. Major manufacturers including Panasonic, Sharp, Samsung, LG, Whirlpool, and GE compete in a global market that sells approximately 40 million units annually. The frozen food industry, worth over $50 billion per year in the United States alone, exists largely because microwave ovens made convenient meal preparation possible. The broader food service industry has been transformed by microwave technology, enabling rapid service models that would be impossible with conventional cooking methods. Yet perhaps the most profound impact has been on daily life, on the texture and rhythm of modern existence. The microwave oven liberated individuals from some of the time demands of food preparation, making it possible to eat a hot meal without extensive planning or cooking skill. This democratization of convenience particularly benefited single-person households, working parents, elderly individuals living independently, and anyone else for whom traditional cooking had become burdensome. Critics point out that this same convenience has contributed to declining cooking skills, to increased consumption of processed foods, to the erosion of family meal traditions. Both perspectives contain truth. Technology rarely delivers pure benefit without some cost, some trade-off between what is gained and what is lost. The microwave oven also exemplifies how military technology transitions to civilian applications, how innovations driven by wartime necessity often find peacetime purposes that eventually overshadow their original use. The magnetron was developed to detect enemy aircraft, to give Allied forces advance warning of German bombers approaching British cities. That same technology now heats coffee in offices around the world, cooks vegetables in suburban kitchens, and keeps late-night convenience stores operating with minimal staff. The transformation from weapon of war to appliance of convenience required not just technical innovation but cultural acceptance, marketing savvy, and the gradual accumulation of familiarity. Percy Spencer never sought to philosophize about the broader meanings of his invention. He saw a problem. Food took too long to heat, and he found a solution using available technology. The metaphysical implications, the cultural transformations, the economic disruptions, these were consequences he could not have fully anticipated and likely would not have considered his responsibility to manage. He was an engineer, a solver of concrete problems, a man who believed that understanding how things worked mattered more than theorizing about what they meant. In this sense, Spencer embodied a particularly American approach to innovation, one that valued practical results over theoretical elegance, that measured success by what could be built rather than what could be proven. His lack of formal education, which might have been a disadvantage in European scientific traditions that prized academic credentials and theoretical rigor, became an advantage in American industrial culture that rewarded productivity and tangible achievements. Spencer never published academic papers, never presented at scientific conferences, never engaged with the theoretical physics community. Yet his practical contributions to radar technology and his invention of the microwave oven arguably had more impact on ordinary people's lives than most academic research. The question of recognition haunted Spencer's later years, though he never spoke publicly about any disappointment. He received awards from Raytheon, from the U.S. Navy, from professional engineering societies. Yet his name remained largely unknown outside engineering circles, while the microwave oven itself became universally familiar. This disconnect between the fame of the invention and the obscurity of the inventor reflects a broader pattern in technological history. Most people can identify Thomas Edison, Alexander Graham Bell, or Henry Ford, but the inventors of equally transformative technologies like the photocopier, the barcode scanner, or the LED display remain unknown despite their invention's ubiquity. Perhaps Spencer preferred it that way. Those who knew him described a man uncomfortable with attention, someone who shied away from cameras and reporters, who found satisfaction in solving problems rather than celebrating solutions. When Raytheon suggested that Spencer appear in advertisements for the Raytheon, promoting the microwave oven with the personal story of its invention, Spencer declined. He believed the product should sell itself on merit, that his role as inventor was complete once the device worked reliably. Marketing was someone else's job. The technical challenges of developing the first microwave oven extended far beyond simply placing a magnetron in a metal box. Spencer had to solve problems of electromagnetic field distribution, ensuring that microwaves reached all parts of the cooking chamber rather than creating dead zones where food would not heat. He had to design door seals that prevented microwave leakage while allowing users to observe the cooking process. He had to develop safety interlocks that automatically shut off the magnetron when the door opened, protecting users from accidental exposure to electromagnetic radiation. Each of these challenges required careful experimentation, multiple prototypes, and occasional failures. The early Raytheon units suffered from reliability problems that nearly killed the product before it could reach the market. Magnetrons would fail after relatively few hours of operation, requiring expensive repairs or complete replacement. The water cooling systems leaked, creating electrical hazards and damaging the devices themselves. Door seals degraded over time, allowing microwave leakage that exceeded safety standards. Raytheon engineers spent years addressing these issues, improving component design, developing better materials, and implementing quality control processes that caught defects before units shipped to customers. Spencer himself remained intimately involved in this refinement process, even as younger engineers joined the project and began contributing their own innovations. He would visit the production floor regularly, examining returned units that had failed, trying to understand whether the failures resulted from design flaws, manufacturing defects, or user error. This hands-on approach, unusual for someone of Spencer's seniority, reflected his fundamental belief that understanding required direct engagement with physical reality, not just abstract analysis of data and reports. The story of the microwave oven's invention intersects with broader narratives about innovation, about how new technologies emerge and diffuse through society. Some innovations are carefully planned, the result of deliberate research programs aimed at specific goals. The Manhattan Project that created the atomic bomb followed this pattern, as did the Apollo program that landed humans on the moon. Other innovations emerge from accident, from unexpected observations that curious minds refuse to dismiss. Penicillin, discovered when Alexander Fleming noticed that a contaminating mold had killed bacteria in a petri dish, represents this pattern. So does vulcanized rubber, discovered when Charles Goodyear accidentally dropped rubber mixed with sulfur onto a hot stove. Spencer's invention fits the accident plus curiosity model, but with an important nuance. The accident, the melted candy, revealed a phenomenon that Spencer's expertise allowed him to understand and exploit. Someone without Spencer's knowledge of electromagnetic radiation, without his experience building and testing magnetrons, might have noticed the melted candy but not understood its significance. The accident opened a door, but walking through that door required preparation, knowledge, and skill. In this sense, Spencer's discovery validates Louis Pasteur's famous dictum, "In the fields of observation, chance favors only the prepared mind." The diffusion of microwave oven technology through society followed patterns that sociologists of technology have documented across many innovations. Early adopters tended to be wealthy individuals and institutions with resources to invest in improving technology and willingness to tolerate inconsistent performance. These early adopters provided the market feedback that manufacturers used to improve the technology, making it more reliable and user-friendly. As reliability improved and prices declined through economies of scale and manufacturing innovation, the technology reached early majority adopters, middle-class consumers who waited until the technology had proven itself but were willing to adopt it before it became universal. The late majority and laggards adopted microwave ovens only after the technology had become essentially standardized, after prices had dropped to bargain levels, after the devices had become so common that not owning one seemed unusual rather than normal. This diffusion process took decades, from the first commercial Raytheon in 1947 to near-universal adoption in American households by the early 1990s. The pace of adoption varied by country, by socioeconomic class, and by cultural attitudes toward food preparation, but the overall pattern remained consistent. Spencer died before the microwave oven reached mass market penetration, before it became the unremarkable appliance that virtually every household takes for granted today. He witnessed the beginning of the transformation, saw the first clear evidence that his invention would become commercially successful, but he could not have imagined how thoroughly the microwave oven would integrate into daily life. In 1970, when Spencer died, microwave ovens remained luxury items, expensive enough that many families debated whether the convenience justified the cost. By 2025, microwave ovens rank among the cheapest kitchen appliances, available for less than the cost of a nice dinner out, so common that college students moving into their first apartments expect to find one included in even the most basic accommodations. The technical principle that Spencer discovered, that microwave radiation could heat food efficiently, has proven remarkably durable. Despite decades of research into alternative heating technologies, despite the development of induction cooking, halogen heating, and other innovations, the microwave oven remains fundamentally unchanged from Spencer's original design. Modern units incorporate electronic controls, improved materials, and better safety systems, but they still use magnetrons generating 2.45 GHz electromagnetic radiation, still rely on metal chambers to contain that radiation, still exploit the interaction between microwaves and water molecules to generate heat. This technological stability suggests that Spencer's insight was not just clever but fundamental, that he had discovered something close to an optimal solution within certain constraints. Microwave heating works because of the specific characteristics of water molecules and electromagnetic radiation at particular frequencies. No amount of refinement can fundamentally improve on this basic mechanism, just as no amount of refinement can make wheels roll better than circles. The innovation space exists in surrounding technologies, in controls, in safety systems, in combining microwave heating with other cooking methods, but the core principle remains Spencer's contribution. The environmental impact of microwave ovens has received increasing scrutiny as concerns about energy consumption and climate change have intensified. Microwave ovens are significantly more energy efficient than conventional ovens for small quantities of food, converting approximately 55 to 64% of electrical energy into heat that actually cooks food, compared to less than 25% efficiency for conventional electric ovens. This efficiency advantage means that heating a single cup of coffee or a plate of leftovers uses far less energy in a microwave than in a conventional oven or even on a stovetop. However, this efficiency advantage diminishes for larger quantities of food and for cooking methods that require browning or crisping, tasks that microwaves perform poorly. The standby power consumption of microwave ovens, the energy they use when plugged in but not actively cooking, has also drawn criticism. Most microwave ovens consume between 3 and 10 watts in standby mode, maintaining clock displays and keeping electronic controls ready for immediate use. Across millions of households, this standby consumption adds up to significant total energy use despite the small per-unit impact. The manufacturing and disposal of microwave ovens also carries environmental costs. Magnetrons contain rare earth elements and metals that require energy-intensive mining and processing. Electronic control systems use circuit boards with various toxic materials. The short lifespan of many consumer-grade microwave ovens, often less than 10 years, means that millions of units enter the waste stream annually, contributing to the growing problem of electronic waste. Recycling rates for small appliances remain low, with most microwave ovens ending their lives in landfills rather than being properly disassembled and their materials recovered. These environmental considerations would likely have surprised Percy Spencer, who lived and worked in an era when manufacturing and consumption were celebrated as unalloyed goods, signs of progress and prosperity. The idea that abundant cheap appliances might create problems as serious as the problems they solved would have seemed pessimistic, even ungrateful. Yet the questions are legitimate and growing more urgent as the planet struggles with resource depletion, waste accumulation, and climate change. The microwave oven exemplifies the challenge of assessing technology's net impact. The benefits are real and substantial, but so are the costs, and determining whether the equation balances positively requires value judgments that science alone cannot answer. Spencer's personal life remained deliberately private, shielded from public attention by his own preferences and by an era when privacy was easier to maintain. He married in 1922, and his wife Louise remained his partner for nearly 50 years until his death. They had no children, and Spencer rarely spoke about his home life in professional settings. Colleagues knew him as focused and reserved, friendly but not intimate, someone who drew clear boundaries between work and personal life. This reticence makes Spencer's inner life difficult to access, his motivations and satisfactions a matter of inference rather than documentation. Did he feel pride in his accomplishments, or did he view them as simply doing the job he was paid to do? Did he understand that his invention would transform daily life for billions of people? Or did he see the microwave oven as just another interesting engineering project? The historical record provides few answers, leaving Spencer himself as somewhat mysterious as the invisible electromagnetic waves he learned to harness. What is clear is that Spencer's approach to innovation differed markedly from the romantic genius model that popular culture often celebrates. He was not a lone inventor working in isolation, experiencing sudden flashes of insight that revealed complete solutions. He worked within institutions, collaborated with colleagues, built on existing knowledge, and refined his ideas through iterative testing and improvement. His success resulted from persistence, from methodical experimentation, from deep knowledge of the relevant physics and engineering principles. The melted candy bar was a starting point, not a culmination. The real work came afterward, in designing practical devices, solving manufacturing problems, and overcoming the countless small obstacles that separate interesting phenomena from useful products. This understanding of innovation as process rather than event has important implications for how we think about creativity and progress. If Spencer's story teaches anything, it is that accidents matter less than responses to accidents, that preparation enables exploitation of opportunity, that curiosity combined with competence produces results that neither quality alone can achieve. The microwave oven was not inevitable. Someone else could have noticed similar effects and dismissed them as irrelevant or incomprehensible. Spencer noticed and pursued the mystery until he understood it well enough to build something useful. The legacy of Percy Spencer extends beyond the specific invention of the microwave oven to the broader principle that unconventional paths can lead to extraordinary outcomes. His lack of formal education, which might have barred him from technical careers in more credential-conscious societies, instead became a distinctive asset in American industrial culture. He learned what he needed to learn, developed the skills the work required, and proved himself through results rather than degrees. This pathway has become more difficult in contemporary society, where formal credentials matter more and opportunities for self-taught individuals have narrowed, but Spencer's example remains powerful evidence that intelligence and determination can overcome institutional barriers. The microwave oven stands now as one of those technologies so common that its revolutionary nature has been forgotten, its presence in virtually every kitchen taken for granted like running water or electric lights. Few people using a microwave to heat leftover pizza or cook a bag of popcorn pause to consider the chain of innovation and accident that made such convenience possible, or to remember the self-taught engineer from rural Maine who refused to dismiss a melted candy bar as mere nuisance. Yet the technology works precisely as Spencer designed it, exploiting the same fundamental principles he identified in 1945. heating food through the interaction of electromagnetic radiation and water molecules. In the end, Percy Spencer's greatest legacy may be not the microwave oven itself, but the example of what curiosity and competence can accomplish when they intersect with opportunity. He saw what others missed, understood what others ignored, and built what others thought impossible or impractical. The microwave oven changed how people cook, how they eat, how they organize their time and their lives. It emerged from World War II radar technology, from a melted candy bar, from one man's refusal to accept mystery. That is how innovation happens, not from genius alone, but from preparation meeting accident, from expertise combined with curiosity, from the willingness to ask why and the persistence to find answers.